Okay, so thanks for the nice introduction. So as Alex mentioned, today we'll be talking about building knowledge graphs with LLMs. And as he mentioned, we're also writing a book with Oscar about knowledge graph rec, but enough of that. So funnily enough, I was looking at the previous session for like 5 minutes, and I saw kind of nice continuation how we're going to continue with this session, because first we're not going to jump straight into knowledge graph building, but we're going to look at when text embedding approach fails, and so and then how to overcome it, right? And then the overcoming will be using knowledge graphs, but as mentioned by the title. But let's just go into when what are the limitations of text embedding approach, right? So in a typical rec pipeline, I've probably seen this so many times now, but basically you take a couple of PDFs, you chunk them up, you index them using any text embedding models, and then at query time, you use the same embedding model, fetch the top 4 or 5 or 10 most relevant documents, pass them to an LLM. You hope that any relevant information is in that document, and then the LLM generates the final answer. But there are some use cases or domains where this approach doesn't really work well, because like this approach really works well for, like, let's say documentation. But for example, for other domains like legal, for some questions, this might not be the best approach, as we'll see, right? And here I have a couple of questions outlined that you can ask. So for example, what are company policies on remote work? But also you can ask other questions like, what's the total value of our contracts with Neo4j or whichever company, right? And we'll see that like different types of questions require different types of approaches, right? So for example, when you're asking what are company policies on a remote work, that's like like I said, like a documentation type of question where basically you just need to find the relevant text chunks that talk about remote work, pass it to an LLM, and you get your answer, right? So that's all good. But like if you're saying like what are payment terms for a specific contract, right? So in this case, if you took like a naive approach and just return top 4 chunks from your vector index, what might happen is that you can get 4, or here I have 3 text chunks from different contracts, which might not be related, and like the LLM could be quite confused, because let's say you get 3 different payment terms for 3 different contracts, right? So in this case, just using naive vector similarity search might already fail. And here in the title, how do I go back? In the title, I can say like this can be overcome, this can be solved by using like metadata filtering. So if your vector text chunks have like some structured data and you can filter by contract ID or company name or something like that, then you narrow down your results, and then you don't get text chunks from different contracts because you used metadata filtering. So that's one scenario where basically you can use structured data to enhance your results. But then, like, if you ask questions like, what's the total value of our contracts with Acme, or like how many contracts expire this month, right? Because this is a question that you might ask if you have like a legal chatbot. And in this case, basically, naive approach, even if you add metadata filtering, completely fails, right? Because the vector index, like rec approach, just returns 4 different text chunks. And like maybe, hopefully, in ideal world, you would get like 4 text chunks with contracts about with Acme that have like the value in it, and then like you would rely on LLM basically doing some arithmetics and adding up the total value. But what if you have more than 4 contracts? What if you have 10 contracts with acme.inc, right? Then in that case, it completely fails, right? And if you ask like how many contracts expire this month, again, basically the 4 chunks that you get from vector index doesn't really help in answering that question. It might like sometimes what we see is that you might get like 1 or 2 contracts that might expire this month, and then the LLM will be okay. Yeah, these 2 contracts expire this month, but that might be like just a partial answer because maybe like 200 contracts will expire this month. But the LLM doesn't know because it gets just for top K text chunks, and you can get inaccurate or partial results. So as mentioned, like certain questions that require filtering, sorting, counting, and aggregating cannot be answered with text embeddings only because basically you need structured data to perform these sorts of aggregations. And then there's one which I didn't really mention before, but like sometimes when you have information spread across multiple documents, the vector approach might also fail because let's say the top K is 3, but all the information is like in 5 documents, right? And then even if your vector similarity search is perfect and it gets the exact information that you want, it's still really hard to define the exact top K because it might be dynamic. Like sometimes you want like 5 documents, sometimes you need 15 documents, and this is mostly like unsolved problem at the moment. So structuring this data can also help with overcoming the top K issue, right? So yeah, this is my first meme, I guess. So basically, when people think or talk about RAG pipelines, mostly they just think about PDFs and documentation and just text, right? But there's like this whole beautiful world of structured data that is like overlooked a lot, and it can help you answer these types of questions, right? Where you need to do structured operations or like for more complex questions, like multi-hop questions. So here, knowledge graphs come into play. So probably you've heard a lot about knowledge graphs today, so we won't go too much into depth about them. But basically, knowledge graphs are used are great at representing structured data, right? So this is probably the most used image to show basically what knowledge graphs are all about. So you can have entities and relationships between them. But this, I think, is now slightly outdated because in the world of LLMs and RAG pipelines, basically what you want most of the time your data sources contain structured information and also unstructured information, right? Because here we only have structured information, but now we want to also bring in additional unstructured information. And the nice thing about knowledge graphs is that you can have both of these types of informations in a single database, right? So for example, here we have a contract and it's linked to 2 companies, and these companies are located in whatever cities. But then, like, for example, if you chunk your contracts by clauses, then you can have each clause in the links to the contract, and you could embed clauses separately and have them linked to the structured part of the graph, right? So basically, you could think about clauses or like your text chunks with quite complex metadata, right? Because the structured part of the graph can be thought about as metadata related to the unstructured part of the graph, right? So basically how I see it now that in the world of LLMs, the nice thing is that you can have both of these types of information together. And that's the power of knowledge graphs. So now let's finally talk about building the actual knowledge graphs with LLMs, right? Because that's kind of a nice thing. Everybody, it's funny, but in LLM world, like 90% of the time, the input is a PDF or a document, right? So we need some sort of way to build a knowledge graph to structure that information from a PDF. And this is what we'll be talking about. So basically, you can have, as I shown before, multiple documents, and then you build a knowledge graph based on the information in those knowledge graphs. And the nice thing about knowledge graphs is that they're very good at combining information about from multiple documents, right? So here we have, let's say, 4 documents that represent this information. But now, if we ask a question, right, like previous OpenAI employees, like which companies they founded, right, this would turn into a very simple Cipher query instead of us having to look through multiple documents, and then maybe like one document contains that the Dario and Daniela worked at OpenAI, and then another document contains that they founded Anthropic. So this is kind of the multi-hop types of questions where you have to look through multiple documents to find the whole truth. And this is also like a very nice use case for knowledge graphs of combining that information in a nice and compact way. And building knowledge graphs from text used to be called information extraction, and it used to be like very complicated. You need multiple models, and each model in the pipeline was very custom and domain specific. So mostly academics did that, or like billion-dollar companies, and nobody in between. But now basically you just ask an LLM, please extract information in a structured way. Mostly the structured way is a JSON, and that's it, right? And so the extracting of structured information from text has become much more mainstream, and that also opens up the possibility of building knowledge graphs from text. And like extracting structured information from text is so frequent use cases with LLM that basically now you have like JSON modes, or like OpenAI also has like structured output mode, and like you can also kind of hack the tools and use them to extract structured output. So basically extracting structured information with LLM is such a frequent use case that there are lots of tools built around LLMs to make it easier for the developers to get like a consistent output. And as mentioned, basically the whole magic of information extraction is that you take some text, some magic happens, and you get like a nice JSON. So basically you get like a nice structured information. And how I see it, basically, the information extraction pipeline, there's like a spectrum of approaches how to do that. And how I see it is like there's the spectrum lies from the most generic extraction, where you have no idea what's in the text, what to extract. You just say LLM extract as much information as possible. And then on the other side, you have very domain specific, where you know exactly what's in the text, for example, legal documents. And you just, you can define each property in the JSON, what it should look like and what should be extracted. So now let's look at the spectrum of approaches and how they actually work in practice. So the first one is the most generic approach, where you have no idea about documents, what's in them, because like a very typical scenario that I see is basically your boss gives you 10,000 PDFs and just says, build a chatbot, and you have no idea what's in them. And in that case, like you could use the most generic approach. You just say, extract nodes which have ID and labels, and extract the relationships between those nodes, and then you hope for the best, right? And this is like such a frequent scenario as well, that you will see a lot of frameworks supporting like the generic approach where you don't have to define any schema. Here I have the code for LangChain because I like LangChain because I implemented that, so I like to show off. So basically, the most generic approach with LangChain just looks like this. You decide which LLM you want to use, and then you pass the document and build the knowledge graph. And here I have one example of a contract between mortgage logic and Rulik Incorporated. So here I ran the extraction on the same contract 2 times, and then you can compare the extraction, right? So now, because we didn't define any schema what we want to extract, you will get very deep, like some relationships might be the same, but some relationships might be different, and like the knowledge graph or the extracted information can be quite different depending on different runs, right? So for example, here we have Rulik hosts a website, and then mortgage logic uses it, and in the first one on the left side we don't have that information. Here we have like that mortgage logic provides credit data and client content, and here we have credit data and client content, right? So some things might stay the same and some things might change, but what we see is that like the schema is very inconsistent, and also the information that's being extracted. And yeah, so basically extraction can be noisy because the LLM decides what to extract, and there's no schema consistency, right? So if you run this extraction on multiple contracts, there is no guarantee that like node labels or relationship types will stay the same. So like then I see it like there's like a middle ground approach where you can define the node labels and relationship types you want to extract. So this requires some upfront work because you need to define what you want to extract, right? But the nice thing is that you can use LLMs to help you with defining the schema, right? Because you can just sample a couple of documents, ask the LLM what types of nodes, node labels, and relationship types did you find in the text, and you just feed that into an LLM, right? And again, you can use LangChain, but it's the wrong code. But basically, what you would do, you would define the types of labels and the types of relationship types. So here you would have allowed nodes and allowed relationships, but somehow I missed that. And then like your schema. So here again, I ran the extraction on the same contract 2 times in a row. So now the extraction is much more consistent between two runs, right? Because we guide the LLM, what do we actually want to extract? Because we guide the LLM more about what information we want to extract, we'll get more consistent outputs, right? There's still some discrepancy between the depth of information between extracted information between different calls, because that's just the nature of LLMs. Sometimes they want to extract more information, sometimes they want to do less. But the nice thing is that we also have like better retrieval options, because now that your schema is more defined, that also gives you better options for the retrieval, because you kind of know what information to expect in the knowledge graph. You also know how to then retrieve it in better ways or more ways. And then the last approach that I kind of like the most is the domain-specific approach. So now basically you define if like you're extracting a JSON, you define every key in the JSON and you give it description. You can give it like available options, like for example dates. You define what's the format that should be used, right? So this type of information extraction requires the most work, but obviously it's the best, gives the best results, right? So here's like one example that you could use to extract information from a contract. So you can have like a type with predefined types and like parties of organizations, dates, like scopes, amounts. And since this is like more like a low-level extraction, there's not like a specific tool you can use, but like you can use frameworks like LangChain, Instructor, Llama Index, or OpenAI structured outputs. You define the information you want to extract using Pydantic objects. And basically with this approach, right, because you define what you want and like you're very descriptive and constrained about the information that needs to be extracted, you will get the best results, right? So here I have basically one example, and then it's basically we have some information as nodes, but then some information is stored as properties as well, right? So for example, this agreement has effective date, like a summarized contract scope and stuff like that. So basically, when you can, so basically this should be domain-specific approach, but basically the LLM is guided exactly on the type of information it should extract, right? And the schema is fixed because it's not actually as before we said to an LLM extract nodes and relationships, but now we basically say to an LLM extract contract type, extract effective date. So the LLM doesn't actually do the graph modeling. The graph modeling is like a separate step. So in this case, like the graph schema is fixed as it's separated from the LLM. And because we can guide and give instructions to an LLM exactly what we want extracted, we'll get the best results. And since the schema is fixed, right, you can create all sorts of tools for the retrieval. So basically, because you know exactly what is in the graph, what's the format of properties and all of that, you get the best options to build like a RAG application that can do all sorts of aggregations, filtering, multi-hop questions, all of that, right? And so that's kind of the 3 types of approaches that I've seen in practice. And now some observations using that in actual practice, right? So obviously, anytime you're going to be building knowledge graphs from text, you'll have to do some cleaning up afterwards. And the most frequent one is the entity resolution. So you can have like multiple nodes representing a single real-world entity. So here in this example, we have like an UTI asset management company. And there are 3 nodes that represent the same node, the same entity. So you want to have like some post-processing steps where you identify these duplicates and merge them. So that way your graph will have much better structural integrity. And then here's some like observations from papers. So this is the paper from Microsoft where they're building knowledge graphs. So like when you instruct the LLM to extract, or let's say, all people and organizations from text, will the LLM actually extract all people and organizations from the text? And the answer is mostly not, right? So nothing is, like when working with LLMs, nothing is really perfect. So then, and they also observed that the extraction is quite dependent on the chunk size that you use. So the smaller chunk sizes that you use, the more information you will extract overall. And another technique that they introduced is that you can do multiple passes on a single text chunk and then extract more information, right? So if you kind of say that on a single pass, we will not extract all the information, maybe let's do 2 passes or 3 passes and try to get as much information as possible. And then this one is also quite interesting, as we've seen before. It is like, how consistent is the extraction? And so even with like a fully defined schema, like let's say domain-specific approach, how consistent is the extraction? And it's like, well, it depends, right, on the types of documents, but the less ambiguous and are the documents, right, the better the consistency will be, right? So here in this example, CVs are the least ambiguous, so they will have the most consistency. And then it's funny, but scientific articles and websites are kind of similar, but we can see that scientific articles are still more consistent because when you're doing science, you shouldn't be as much ambiguous as you can be when you're basically doing websites. And one thing that's also quite interesting to see is that nobody this is like an evolving space, and nobody really knows what's the best approach to extracting knowledge graphs or like structured information. So like, then you have so many options how to do, like you can use JSON modes with LLMs, you can use tools, functions, you can just do regular prompts and define the example with few shots. And basically, this is all very model specific, so it's really hard to say what works best because it really depends on the model and not just like the model, let's say, because even like GPT-4o from January behaves differently than GPT-4o from April. But this is also something to think about when you're building knowledge graphs. And that's it for me. So just on time. And now we have 2 minutes for questions. And basically also, because this is like a theoretical talk, but if you want some code so you can try it out, you can go and look at my blog posts or code examples and test it on your own. So yeah, now I don't know if we have time for questions.
We can probably squeeze one in. Thank you, Tomaz. The one with the most votes comes from Raya. And they ask, how does a knowledge graph update internally when I add new document to the graph?
Yeah, I mean, so that's basically up to you. But build like adding additional information is not not a big problem because it's just adding additional nodes and relationships. But the only thing you have to be careful is that you do entity resolution, right? So if an entity is mentioned in the text that's already in the graph, you kind of want to use the same name because, as mentioned, like sometimes not exactly the same name is used. So then the only problem is dealing with this. But like this could also be like as post-processing, you update your knowledge graph and then try to search for duplicates. But other than that, it should be very straightforward.
Yeah, cool. And then there's one more, maybe we can squeeze it in as well from David. And we'll keep on answering this one and then we close it. But if you need to jump to the next session, you can do so. What is your recommendation to perform graph disambiguation, merging duplicated nodes or different nodes that are actually the same thing?
Yeah, so what you see in practice is that, I mean, it really depends on the types of nodes you want to like merge together. So it's very different when you're merging people than when you're merging organizations or locations. But for the most part, what we've seen is that you use text embeddings to find potential candidates that could be merged. And then you can use some sort of like word distance, or like you can have like an LLM as a judge deciding if an LLM, if two entities should be merged. So kind of the generic approach is that you use a combination of text embeddings and then additional logic to give the final decision if two entities should be merged or not.
Super. Cool. With that, I think we're at the end. Thank you very much, Tomaz. Thank you for watching. Keep continuing with the notes presentations throughout the day, and yeah, see you at the next session and somewhere in the future. Bye. See you later.